You know, it's funny. Sometimes the biggest challenges in physics remind me of trying to catch a firefly. The problem isn't seeing it, it's actually catching the thing without it vanishing. And that feels like a good way to think about antihydrogen.
It's a perfect analogy. Antihydrogen, or ESPAR as we call it, is the only pure anti-atomic system we've ever been able to study. But making it and then trapping it in a magnetic bottle before it just annihilates, well, that's been the challenge for decades.
And it's so important because it's our best shot at seeing if there's any difference, even a tiny one, between matter and antimatter, right? To explain why, we're here at all.
That's the billion-dollar question, yes. Since the universe is all matter, any slight difference could be a clue.
Okay, so that brings us to this huge breakthrough at CERN with the Alpha experiment. They didn't just get a little better at catching these fireflies, they built a much, much better net. Let's break down this new cooling technique.
Right. So the core of the problem has always been making the antihydrogen cold enough to trap. You do this by merging these cold plasmas, one of antiprotons, the other of positrons, which are anti-electrons.
And the antiprotons have to cool down by interacting with the positrons.
Exactly. So the positrons have to be incredibly cold. If they're even a little too warm, the antihydrogen they form is too energetic, it's too fast.
And it just shoots right out of the magnetic trap.
Gone instantly. And researchers had really pushed the traditional cooling methods, like evaporative cooling, to their absolute limit. They were stuck.
When you hit a wall like that, a technical plateau, you often need to look outside your immediate field for a solution.
Absolutely. And that's what happened here.
And finding those cross-disciplinary solutions is so key. This deep dive is sponsored by EmberSilk. If your business needs help with AI training, automation, or custom software, or you're just trying to figure out where AI agents could make the most impact, check out embersilk.com. They really specialize in tackling those kinds of complex technical problems.
So the breakthrough idea was a technique called sympathetic cooling. The ALPHA team brought in a totally separate cloud of ions, laser-cooled beryllium ions specifically.
Okay, so they're not mixing them in directly.
No. Not at all. The beryllium ions act like a refrigerator, but kept in a different part of the trap.
And this is where it gets really interesting, right? The beryllium ions and the positrons, they're both positively charged, so they repel each other.
They do, and they interact through their electric fields. It's called Coulomb coupling. It basically creates a kind of friction. The super cold beryllium ions just suck the heat right out of the positron.
And the result was just, wow.
It was. They cooled the positron plasma down to around 7 Kelvin. That's colder than deep space.
And about 2.5 times colder than they'd ever gotten before.
Which was the final proof. It confirmed that the positron temperature was the real bottleneck all along.
I have to ask, though, if you're bringing beryllium ions into this pristine environment, isn't there a risk of, contamination?
That's the elegant part of the design. The beryllium is kept physically separate from where the antiprotons are. It cools the positrons before they are mixed to make the antihydrogen. It's a clean external refrigeration system.
And the payoff was this 8-fold increase in how fast they could accumulate atoms.
A huge payoff. They managed to trap over 15,000 antihydrogen atoms in less than 7 hours.
Okay, stop there. For perspective, getting that many atoms for a previous big measurement took them 10 weeks.
10 weeks, yes. So you go from a time scale of months to a time scale of hours. It's a complete revolution for this kind of research.
So what does this actually mean for the future? What can they do now that was impossible before?
Well, with this kind of speed, you can start doing systematic studies. You can hunt for really subtle effects, like something called sidereal variations.
Which is checking if the properties of antimatter change based on where the Earth is pointing in the galaxy.
Precisely. It's a test of one of the deepest symmetries we assume about the universe. It requires incredible amounts of data, which they now have.
And it must be a huge boost for the gravity experiments too, right? The ALPHAG experiment.
Oh, absolutely. Directly measuring how gravity affects antimatter demands massive statistics. This is exactly what they needed. The ultimate goal is to get to the same precision we have for regular hydrogen.
We're talking about measuring its properties to something like 4 parts in a quadrillion?
That's the target. Only at that level of precision can we say, for sure, whether matter and antimatter are truly perfect mirror images.
And looking forward, this feels like it unlocks so much more. The idea of creating actual beams or even fountains of antihydrogen, It suddenly doesn't seem like science fiction.
It's a clear path forward. It really is an inspiring example of ingenuity. The big breakthroughs sometimes come from just finding a clever new way to make something colder.
It's fantastic to see that kind of progress. If you enjoyed this deep dive into the fascinating world of antimatter, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.